Principles of Bioproduct Separation, Module 13, Drying, Segment 4, Adiabatic Drying. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about basic concepts of drying, drying equipment, and conduction drying. In this segment, we will discuss about adiabatic drying. Let's consider that we are drying one wet solid particles in a stream of excess dry air, and the results are shown in the following figure. Figure in the left shows the particle weight versus time, whereas figure in the right shows drying rate versus the water content. At first, the water content drops linearly with time with a constant drying rate. Later, the water content drops more slowly, indicating that the drying rate at low water content is also lower. And the initial linear region is called the constant rate period, and the later low moisture zone is called the falling rate period. The water concentration where these two periods meet is called the critical moisture content. Free water in the solid has the properties of pure bulk water and can move by capillarity within the solid. When the air has constant properties, the free water evaporates at a constant rate, just as pure bulk water does. When this free water is exhausted, the bulk water will begin to evaporate. Because it is immobile, it must evaporate within the particle and then tortuously diffuse out of the particle and into the surrounding gas. Such bulk water will move more slowly and hence retard the drying rate. This result suggests that the total drying time will be the sum of the times of constant rate drying and of falling rate drying. The time for constant rate drying can be calculated by first considering a mass balance on the same single particle of diameter d as shown in equation 17. The equation can be simplified in two ways. First, if the particle has a fixed diameter, d is a constant. Second, if the water vapor is always greatly diluted by the air, the flux can be expressed by equation 18. The drying rate can be estimated in terms of humidity as shown in equation 19. Because the drying is adiabatic, the heat conducted from the air to the particle is proportional to the amount of water evaporated, can be expressed using equation 20 and equation 21. Upon integration of equation 21, the drying time can then be calculated using equation 22. Falling rate periods may involve only a relatively small amount of water but may take a large fraction of time. This is because the water may need to diffuse out along some slow tortuous path. It may require a heat of vaporization which is both larger than that of free water and a function of the remaining water content. As a result, the analysis of the falling rate period is complex. The drying rate can be approximated by equation 23. Upon integration, the incremental time for the falling rate period as shown in equation 24. Combining with equation 22, the total drying time can then be calculated using equation 25 and equation 26. For a better visualization about drying, students may want to check these videos on YouTube. Until then, I am Yusuf from Institut Teknologi Bandung.